Hello everybody, welcome to Shaders Monthly. Today we talk about procedural noise. In particular, we will learn how to generate value noise that you see on the left and color gradient noise that is shown on the right. Furthermore, we will see that we can add multiple layers of noise with different frequencies and amplitudes to generate noise with more details. This approach is often called fractal noise. On the left you see fractal value noise and on the right fractal gradient noise. To implement the procedural noise functions in GLSL, I use the GSN Composer at gsn-lib.org as a shader editor, but you can use any other shader editor as well. We are writing pure OpenGL GLSL code which you can use everywhere. Links to examples that execute the same shader code using C++ or Java can be found in the video description. Our implementation starts with our example from episode number 5, in which we have applied a 2D texture to a triangle. Click Project and type in the project name Shaders Monthly 05 and click Open Existing. Then open the graph texture triangle and press play in the time control panel. Let's replace the triangle with a quad. Click Create and navigate to 3D, Compute, Generate, Plane. Then we connect the mesh data node to the mesh input slot of the shader node. Perfect, we are rendering a quad that exactly fits the size of the frame buffer. The currently applied texture is this image here. Let's have a look at the shader code. We select the shader node and click the Edit Code button. This dialog is a shader editor of the GSN Composer. In the top section we can define the vertex shader, and in the bottom section the fragment shader. Here we have the uniform variable sampler2D_my_texture that represents the pixel-based input texture. In the fragment shader we use the built-in GLSL texture function to get a color value from the texture. The first parameter is the sampler2D variable and the second parameter is the current texture coordinate. The next line writes the texture color to the frame buffer pixel. Uniform sampler2D_my_texture can be removed. We replace texture my_texture with the function value noise and define the function vec4valueNoise. The texture coordinates are passed via a vec2 that we call pos. vec2pos. We first simply return the texture coordinates in the red and green channels. Return vec4 pos.x, pos.y, 0.0, 1.0. We see at the shader output that the texture coordinates are in the interval from 0 to 1 in both dimensions. A texture coordinate of 0, 0 is at the bottom left corner, 1, 0 at the bottom right corner, 0, 1 at the top left corner, and 1, 1 at the top right corner. First of all, we need a function that generates some pseudo-random numbers. It is called pseudo-random because the numbers appear to be generated statistically by a real random process, but in fact are generated by a deterministic function. Because it is a deterministic function, it produces the same numbers for the same input parameters. To select a good pseudo-random number generator, I would like to refer to a paper called Hash Functions for GPU Rendering by Mark Jasinski and Mark Olejno, published in the Journal of Computer Graphics Techniques in 2020. The authors compare different random number generators for quality and speed. I paste the code of a random number generator that they recommend into our shader. We see that this function is expecting a uvec3 as input, which is a vector of 3 unsigned integers. The output is a vec3, a vector of 3 floating point values. This means that we get 3 random numbers from one function call. These output numbers have a uniform distribution in the interval from 0 to 1. Our first goal is to output a random color for each pixel of the output frame buffer. As we have learned in previous episodes of Shaders Monthly, the fragment shader is called for every pixel of the output frame buffer. To convert the texture coordinates to pixels, we add the function t2p. Now the current pixel in x direction can be computed by float px equals t2p pos.x comma width, and the current pixel in y direction by float py equals t2p pos.y, comma height. Furthermore, we need to define uniform int width and uniform int height to get the width and height of the frame buffer. Now we can use px and py as seeds for the random number generator. vec3 random equals random underscore pcg3d uvec3 px py 0. Return vec4 random 1.0. We return random as the RGB value and 1.0 as the alpha value. Okay, this looks good. For every pixel we get a different random color as output. Now when we change the seed here, for example when we put 1 instead of 0, we get different random values. 2, 3, every time we get different values. Let's animate this value. We add a uniform variable, uniform int graph time. Apply code and close. The input texture can be deleted. We create the node input compute time, and in the time control dialog, which we can reach via this button, we set the end parameter to a larger number, for example 20,000. Furthermore, we increase the rendering speed and set the parameter milliseconds per tick to 20 milliseconds. Next, we connect the data output of the time node to the input slot graph time of our shader. We open the shader editor again and put graph time as the third seed of the random number generator. Perfect, now we get new random values for every rendered frame buffer image. For many applications, this noise output is too chaotic. There is no correlation between neighboring values. These are just random numbers from a uniform random number generator. To change this, we are now implementing value noise. The idea is that we are not generating a random value for each pixel. Instead, we generate a random value for points on a coarser grid. To this end, we subdivide the complete domain of texture coordinates into an 8x8 grid. We compute a grid position. Const float grid size equals 8.0. vec2 grid pos equals pos times grid size. If pos is in the interval from 0 to 1, grid pos is in the interval from 0 to 8. To get the integer part of grid pos, we cast to a uvec2, which is a vector of two unsigned integers. uvec2 I equals uvec2 grid pos. With this operation, we round downwards to the nearest integer, which gives us the digits before the decimal point. We also need the fractional part of the grid position. vec2f equals fract grid pos, which gives us the digits after the decimal point. Consequently, the values of f are again in the interval from 0 to 1. Let's output f. Return vec4 f.x, f.y, 0.0, 1.0. As you see here, we get an 8x8 grid, and inside each cell, the variable f goes from 0 to 1 in both dimensions. This is a grid size of 16 by 16, 4 by 4, and back to a grid size of 8 by 8. Now, if we use the integer value of each grid cell as seeds for the random function, we get the same random value per grid cell, although each grid cell consists of many output pixels. uvec3 i.x, i.y, 0. Apply. Okay, let's use the graph time variable to translate the grid cells over time. vec2 pos equals interpolated text coord plus 0.002 times float graph time. Value noise pos. Well, this looks nice. It is a never-ending stream of random colors that only repeat when graph time repeats. The value of graph time repeats when it reaches the end of our animation time, which we have set to 20,000. Let's stop the animation. To generate value noise, we need a smooth interpolation between the grid colors. One interpolation technique that we already have learned in episode number 6 is the bilinear interpolation. The bilinear interpolation is computed from 4 neighboring values, which are the random colors in our example. The dashed lines represent the coarse grid of our random variables. To compute the interpolated value at the location of the blue point, we first interpolate in x direction using the x position of the blue point within its neighbors. This is done 2 times, for the 2 neighbors at the bottom, resulting in a linear interpolated value at this new point, and for the 2 neighbors at the top, which gives us a result for this new point. Once this is done, we perform linear interpolation in the y direction, using the y position of the blue point within the 2 new points. The same setup is now illustrated in a 3D figure. The grid is the ground plane and the color values are represented as these red bars that point upwards. The length of the red bars corresponds to the stored random values. Now we first compute the value at location Q1 by linear interpolation. And here's the equation to perform this operation. You see that we use the values at x1, y1 and x2, y1 to perform this operation. Next, we compute the value at location Q2 by linear interpolation. The value at x1, y2 and x2, y2 are used. And finally, the linear interpolation in the y direction where the values at Q1 and Q2 are used. To implement this linear interpolation in our shader, we need the 4 neighboring random values. f11, ix, iy, vec12, ix plus 1, iy, f21, ix, iy plus 1, f22, ix plus 1, iy plus 1. To perform the linear interpolation, GLSL has a built-in mix function. The first 2 parameters are the values that are interpolated, and the third argument is the interpolation weight. To compute Q1, we interpolate f11 and f12 in x direction. Vec3 Q1 equals mix f11, f12, vec3 f.x. Return vec4 Q1 1.0. Apply code. Same for Q2, vec3 Q2 mix f21, f22, vec3 f.x, and then interpolate in y direction. vec3p equals mix Q1, Q2, vec3f.y. Return vec4p 1.0. Good, this is the correct interpolation result. But it looks a bit blocky. We can fix this by using the built-in GLSL smooth step function. The smooth step function is shown on the slide. It implements a nonlinear smooth transition from 0 to 1. The first parameter defines where the transition starts and the second parameter where it ends. We needed to map the complete fractional part, so we have f equals smooth step 0.0, 1.0 f. Excellent, this looks better. Let's turn on the animation. We refactor the code. Vec3 value noise, vec2 pos float grid size. Return p. And we define a new function, vec3 fractal value noise, vec2 pos, vec3 n equals vec3 0.0, n plus equal value noise pos 8.0, return n. And call it in the main function, vec3 text color equals fractal value noise pos. Out color equals vec4 text color 1.0. Okay, this should not change anything. Apply, recompute, no change. The idea of fractal noise is that we sum up noise with different frequencies. which means here different values for the grid size parameter. A common approach is to double the frequency and take half the amplitude for every layer. So let's try n plus equal 0.5 times value noise pos 4. Apply. We add the next layer, n plus equal 0.25 times value noise pos 8.0. And another layer, n plus equal 0.125 times value noise pos 16.0. The layers are also called octaves. Same as in music, the frequency doubles for every octave. But you don't have to follow this rule and can freely play around with these values to produce the noise characteristics that you need for your application. Obviously, the computational effort increases with every layer that we add here. Let's output the pure value noise again. We comment this line and type vec3 text color equals value noise pos 4.0. Apply and close. We name the shader value noise. Now the second type of noise that we introduced today is gradient noise. Gradient noise was introduced by Ken Perlin in a SIGGRAPH paper in 1985. We copy the value noise shader and reconnect the inputs. We call this shader gradient noise. We open the shader editor for this new node. We rename the functions to gradient noise and fractal gradient noise. The idea of gradient noise is shown on this slide. Instead of interpolating random values, we interpolate between gradients. At each grid point, we create a gradient vector in a random direction of random length. The interpolation part stays exactly the same. How can we compute the gradient vector's influence at each position within the grid? Let's look at a single gradient. For simplicity, this gradient vector that we have selected has unit length. The value of the gradient's influence at each position can be computed with a dot product. The red arrow represents the random gradient vector and the blue arrow is the vector to the current interpolation point. If we take the dot product of these two vectors, we get a value of 0 if the two vectors are perpendicular, a negative value from 0 to -1 if they point in opposite directions, and a positive value from 0 to 1 if they point in the same direction. Overall, within this unit circle, we get a linear gradient from -1 to 1. There are different options for the generation of the gradient vectors. The approach that I present here creates a random vector by randomly picking a point within the unit circle. Given an angle phi and a radius r, the x and y position of a point within the unit circle can be computed by x equals r times cosine phi and y equals r times sine phi. We start from two uniformly distributed values u and v in the interval 0 to 1. Let's first try to assign u to the radius and phi equals 2 pi times v. We see that we don't get a uniform distribution over the area of the circle. The sampling points are concentrated at the center. What we want is a constant sample density over the complete area. But the area of a circle increases quadratically with the radius. We can compensate for this by assigning the square root of u to the radius. This gives us a uniform sampling. Now that we have discussed the theory, the implementation is not complicated. We copy this code block and comment out these lines. We changed the last parameter from 0 to 1 because we want different random values for our gradient vectors. We replace random PCG3D with a new function that we call random gradient. The output of this function is a vec2, and we call the variables vec2g11, vec2g12, vec2g21, vec2g22. Next we define the random gradient function. Define mpi 3.14 and so on. Vec2 random gradient u vec3p, vec3uv equals random pcg3dp, float r equals square root uv0, float phi equals 2 times mpi times uv1, return vec2 r times cosine phi, r times sine phi. Next we compute the influence of the gradient at the current interpolation value f with a dot product, as discussed in the slides. Float d11 equals dot g11f. Float d12 equals dot g12f. For d12 we should not use f directly but use the offset relative to the next grid position to the right, which is minus vec2 1.0, 0.0. Then for the grid position above, float d21 equals dot g21 f minus vec2 0.0, 1.0. And lastly, float d22 equals dot g22 f minus vec2 1.0, 1.0. To use the same interpolation code as before, we have to cast the float values to a vec3. vec3f11 equals vec3d11, vec3f12 equals vec3d12, vec3f21 equals vec3d21, vec3f22 equals vec3d22. Apply code. Okay, this looks good, but we might get negative values, which we can prevent by adding 0.25. Gradient noise done. But the output is not very colorful. To add colors, we can combine value and gradient noise. We comment out these lines and uncomment the code that we have used for the value noise. There are different ways to combine both approaches. Let's simply multiply our random values and the gradient before the interpolation. Remove plus 0.5 here and add times d11 plus 1 times d12 plus 1 times d21 plus 1 times d22 plus 1. Apply. Excellent. If we compare both approaches, the gradient noise looks more natural and less regular. For the value noise, the underlying grid structure is more obvious. Let's enable the fractal noise variant for the gradient noise. Looks also good. Today we have learned how to generate value and gradient noise. This is an important building block for future episodes of Shaders Monthly. We are going to use procedural noise functions to create things like water waves, clouds, fire, and so on. If you have questions, use the comments or get in contact with me. See you at the next episode of Shaders Monthly.